Section 7.2 is properties of exponential functions. Our goal is to graph exponential and logarithmic functions showing intercepts and behavior and amplitude. On page 515, we have you can apply the four types of transformations, stretches, compressions, reflections, and translations to exponential functions. The factor a in y equals a times b to the x power can stretch or compress and possibly reflect the graph of the parent function y equals b to the x power. The graphs of y equals 2 to the x in red and y equals 3 times 2 to the x in blue are shown. Each value of y equals 3 times 2 to the x is 3 times the corresponding y value of the parent function y equals 2 to the x. So over here we have a table of values. We chose negative 2 to 2 as our x, and then we plug the x's in to both the parent function y equals 2 to the x and our new function y equals 3 times 2 to the x. You can see in the table that all the values in the third column are just the values in the middle column multiplied by 3. We can also see that there is a stretch in the graph. Our red graph is the parent function y equals 2 to the x power, and we are stretching the blue graph up vertically by a factor of 3. Example 1 says, how does the graph of y equals negative 1/3 times 3 to the x power compare to the graph of the parent function? The first thing we should note is that the parent function is y equals 3 to the x power. Next, we can make a table of values for both the parent function and our new function y equals negative 1/3 times 3 to the x power. If we plug in negative 2 to our parent function, we get 3 to the negative 2, which ends up being 1/9. If we plug this in to our new function, negative 1/3 times 3 to the negative 2, we get negative 1/3 times 1/9, which gives us negative 1/27. If we plug in negative 1 to the original, we get 3 to the negative first, or 1/3. If we multiply this by negative 1/3, we end up with negative 1/9. If we plug in 0 to our parent function, we get 3 to the 0 power, or 1. If we multiply this by negative 1/3, we get negative 1/3. If we plug in 1 to the parent function, we get 3 to the first, or 3. If we multiply this by negative 1/3, we get negative 1. If we plug in 2 to the parent function, we get 3 squared, or 9. And if we multiply this by negative 1/3, we get negative 3. If we plot all the coordinate points from the first two columns, we get negative 2 and 1/9. That should be pretty close to above the x-axis. Negative 1 1/3 should be about a third of the way. 0, 1 will be right at 0, 1, 1, 3, and 2, 9. Now if we plot the coordinate points from the first column and the third column, we get negative 2, negative 1/27, which should be very, very close to the bottom of the x-axis. Negative 1 and negative 1/9, which should be a little bit further away. 0 and negative 1/3 should be about a third of the way down. 1 and negative 1, and then 2, negative 3 would be down here a little bit. The negative 1/3 in y equals negative 1/3 times 3 to the x power reflects the graph of the parent function y equals 3 to the x power across the x-axis and compresses it by a factor of 1/3. So our parent function was above the x-axis. When we have that negative 1/3, it's going to reflect over the x-axis, so now it's on the bottom. The parent function was further up from the x-axis than the reflected negative 1/3 in our new function is much closer to the x-axis. The domain and the asymptote remain unchanged. Notice the domain for both of these functions is all real numbers. I can still plug in any x value that I want. The asymptote is still the x-axis. The red line is going to get really close above, the blue line is going to get really close below, but neither of them will ever touch the x-axis. The y-intercept does change. It was up at 1, now it's down at negative 1/3. And the range, instead of being all the positive numbers, is now going to be all the negative numbers. The work for this problem is written out on the next two slides. And now I would like you to try number 1, graph the function y equals negative 5 to the x power.